We are continuing the notes on gas laws. This is part 3, so you should have already watched part 1 and 2, and we're continuing with a couple more of the little gas laws on this one. In science, a lot of times we want to understand a phenomenon. If we see something, we want to understand why did that happen. For example, a snow-capped mountain. You can have a mountain with snow up on top even in a very warm climate, like for example, on the equator, like Mount Kilimanjaro in Africa. Why does this happen? Well, this can be understood from gas laws, actually. So when we think about the application of gas laws, it really comes down to understanding the way that gases behave in the world around us. Our third gas law that we're looking at is called Gay-Lussac's law, named after a scientist named Gay-Lussac. And it relates two of the measurable properties of gases, the pressure and the temperature of a gas. Notice that some things are left out of this equation. Volume is left out and moles is left out. So that means you can't change the volume and you can't change the moles, but guess what? That's actually easy. Just put the gas in a tank, and then as long as it doesn't leak, you get the same amount of gas in there, nothing's coming in or going out, and you've got a constant volume if the tank is not flexible, that is. So Gay-Lussac's law states that there's a relationship between pressure and temperature. P1 over T1 equals P2 over T2. Notice this looks a lot like one of the other two gas laws that we've already seen. Which kind of relationship do you think this has? Just looking at it mathematically, maybe now you can begin to see what a direct relationship looks like. This is a direct relationship. That means that if the temperature increases, the pressure increases. Or in the case of going up a mountain, what's really happening is the pressure is decreasing, causing the temperature to decrease. They call that adiabatic cooling, which is why it's very cold at the top of a mountain if it's high enough compared to the base of the mountain. And if it's colder, well, you're much more likely to have snow instead of rain, or to at least have that snow not melt once it's on the surface. And that goes a long way to explaining why we have snow-capped mountains. Gay-Lussac's law. So Gay-Lussac's law says that there is a direct relationship between pressure and temperature if you have a constant volume. And of course, we already stated you also need to have a constant number of moles. You can't change anything that's not in the equation, or you have to throw the equation out the window. This equation is the first one we've seen that can be practically applied in the real world as long as you're dealing with a container with a constant volume and no leaks, as I said before. In a direct relationship, again, the two quantities do the same thing as each other. So in other words, if one increases, so does the other. If one decreases, so does the other. If one of them is doubled times 2, so is the other. If one of them is divided by 10, so is the other. They do the same thing proportionally. Okay, that is why it is called a directly proportional relationship, or a direct relationship for short. So direct relationships occur all the time. They're easy to understand. They're the kind of relationship we usually assume, okay, when we are talking about how things are related. That's the one we often assume unless we know better. So luckily, this has a direct relationship, easy to understand. Here we see a graph of pressure versus temperature for a gas at constant volume. This is really Gay-Lussac's law. This, of course, is a direct relationship. It's a positively sloped line like déjà vu. You saw this before. Looks very similar to the graph we saw for Charles's law, except for now we're talking about pressure and temperature instead of volume and temperature. Now, pressure and temperature, as I told you, are very, very linked together. They're very intrinsically linked together, but volume isn't. So you can leave volume out and still get a pretty good result. As long as you have a constant volume, like a tank, and a constant moles like no leaks, then this law actually works. So let's look at a set of conditions. At 100 Kelvin, the pressure is 1 atmosphere, 1.0. Now notice 100 Kelvin, that's very cold, and 1.0 atmospheres, well, that's just normal atmospheric pressure. That's about what the pressure is all over the Earth near sea level. It's very close to 1.0 atmospheres. That's what we normally experience living on the surface of the Earth. Okay, if you divide those, that pressure 1.0 divided by that temperature 100, P over T, what you get is a quotient of 0.01 atmospheres per Kelvin. That's 1/100th atmosphere per Kelvin. So notice that's a really weird unit. We often encounter strange units in the middle of solving a problem. You never have those weird units as one of your answers. Now let's move on up to 200 Kelvin. Well, at 200 Kelvin, now the pressure has doubled to 2 atmospheres. Well, that is a lot more than you would ever get on the surface of this planet. And that temperature is kind of cold, colder than you would normally experience on the surface of this planet. But still, if you divide the 2.0 atmospheres by the 200 Kelvin, guess what? You still get the same quotient, 0.01 atmospheres per Kelvin. So notice that that's a constant. The quotient of the pressure divided by the temperature is a constant in Gay-Lussac's law for a particular volume in moles of a gas. What if we went up to a more normal temperature? Okay, 300 Kelvin actually is a temperature that we would experience in our everyday lives. It's just warmer than room temperature. It's colder than body temperature. And at 300 Kelvin, the pressure is 3.0 atmospheres. But again, if you divide 3.0 by 300, you get 0.01 atmospheres per Kelvin. So notice, this quotient is a constant, and that's the reason that Gay-Lussac's law works. So if you double the temperature or even triple the temperature like we did here, well, then you double the volume or triple the volume. The same thing happens. Or what if we started with the 300 degree one and we went down to the 100? So that would be dividing the temperature by 3. Well, then we would, of course, divide the pressure by 3. It's directly proportional. It's a direct relationship. Here's an example of a Gay-Lussac's problem, a very typical Gay-Lussac's problem. Solve for P2 when P1 is 1.00 atmosphere, T1 is 50 degrees Celsius, and T2 is 100 degrees Celsius. Well, you know what? We don't have to solve this, do we? Because just looking at that, you can see that the temperature doubles from 50 to 100, right? It's a direct relationship, right? So the pressure's got to double to 2.00 atmospheres, right? Actually, no, that is wrong. You should see why that is wrong. Because Celsius is not the scale that we use in gas laws. Celsius is not the total temperature. We're not really doubling the temperature there like that makes it look. That is another reason we have to convert to Kelvin, not just to avoid zeros. So what is 50 degrees Celsius in Kelvin? What do I have to do to that to make it into Kelvin? What do I add? 273. 273 plus 50 gets me to 323 Kelvin. What about 100 degrees Celsius? What would that be in Kelvin? Well, I add 273 to 100. I get 373 Kelvin. So those are my temperatures. Those are the only ones I want to see you put into a Gay-Lussac's problem. Never put Celsius in there. That's a very bad idea. Not even for a moment, not even to put it in and then convert it. Just convert them to Kelvin before you even put them into the equation. And then, well, P1 is in atmospheres, that's fine. You know what? Gay-Lussac's law is very forgiving for the pressure. The pressure could be atmospheres, it could be kilopascals, it could be whatever, PSI, it could be whatever. So now let's put those in. For the pressure, we're starting off with 1.00 atmospheres, and we don't know P2, that's our unknown variable. And for the temperatures, we're starting with 323 Kelvin, and we're ending up with 373 Kelvin. That's our T1 and T2. So now, what's the way to solve this again? What's the recommended way that I gave you? What's the best way to solve this? Even though our variable now is in the numerator, so it wouldn't be so hard to do so, I still recommend using cross multiplication. It's just a better way to do it. You never have to worry about it. If you use cross multiplication, it works every time. So even in this situation, I'm going to recommend cross multiplication. So what's the first thing we do? Which two numbers do we multiply? The numbers that are diagonal from each other. The two quantities that are diagonal get multiplied together. That's step one. So 1.00 times 373, of course, is 373. And then the unit is atmosphere Kelvin, a weird unit. Step two, what do I do next? Oh yeah, there's this one other number here. I got to do something with that. What do I do with that number? I divide by it. So that's the odd number out, the leftover number. You divide what you just got, the product of what you just got, by the leftover number. Divide by the remaining number. Well, 373 atmospheres Kelvin divided by 323 Kelvin, well, the kelvins are going to cancel. All that we're going to have as our unit is going to be atmospheres. And, oh, it's not going to be like a big number because actually they're very slightly different. 373 and 323, that's not dividing by a number that's half the size. So we're not going to get a number that's all that different after all. What we're going to get is 1.16 atmospheres. That is my P2. So P2 equals 1.16 atmospheres. I'm rounding it to the hundredths place, as you should. If you're given information, look at the question. If I'm only given information to the hundredths place, then I only want to give my answer to the hundredths place. Generally, that's a good rule of thumb. So notice we just solved for P2, and no, it did not double the pressure because we did not really double the temperature. That thing at the beginning, that was sort of a psych out because that's just to show you that the temperature in Celsius is not the total temperature. Always use Kelvin. The gas law that we will look at is Avogadro's law, named after the great chemist who specialized in studying gases. Avogadro's law is V equals Kn. Now looking at that, you would imagine, oh, that's three variables. But actually, one of them, K, is not a variable. That's why we haven't seen it before. It is actually a constant. Constants are our friends. Constants are numbers we can rely on. We know what they are. They don't change. They're not wishy-washy like variables. So V, we know what V is, volume, the space occupied by a gas. N, what does N stand for? Oh yeah, that's moles. And this is the first time we've seen moles in one of these equations. So V equals Kn. So if you know how many moles you have, you can figure out the volume of the gas if you multiply by the constant K. The constant K has the value of 22.4 liters per mole. That is what we call the mole box. A mole box is a box that's about a little more than about a foot on a side and perfectly square. And in that volume, you have about 22.4 liters. So for example, if I had 1 mole of a gas and I multiply it by K, well then my V would be 22.4 liters. That's the volume of 1 mole of a gas. That's really what Avogadro's law is saying. And then any other number of moles, like 2 moles, 2 times K will give you the volume of that gas. So the problem with Avogadro's law is it's extremely restricted, much more restricted than the other gas laws we've seen because of what it leaves out. Notice that it leaves out both temperature and pressure. So Avogadro's law only works if temperature and pressure don't change. Not only that, if you want to use this value of K, well then they can't just not change. The temperature and pressure have to be at an exact set of values that we call STP, standard temperature and pressure. Standard temperature and pressure has been assigned as 0 degrees Celsius and 1.0 atmosphere. That's a little bit colder than we normally get, especially in Southern California. That's about where water freezes, 0 degrees Celsius. And that's our normal atmospheric pressure. 1.0 atmosphere is what we normally have anywhere on Earth near sea level like we are. And it turns out it only works at those conditions. So Avogadro's law is an extremely restricted gas law, making it pretty easy to use. Amedeo Avogadro came up with this idea that gases are all acting kind of the same. If they're under the same conditions like pressure and temperature, and if you have the same amount of volume, you'll have the same number of moles. That's basically what he suggested. And this was the original way that they began to figure out molar masses. A result of this relationship is that molar masses can be easily determined. Some of the first molar masses that were determined for gases using this gas law. His law, if you put it in a sentence, is that 1 mole of a gas occupies 22.4 liters at STP. Again, that is the mole box. It's a box about 1 foot on a side that holds about 22.4 liters. So Avogadro was basically saying that gases, they're all the same. Doesn't matter the identity of the gas, like whether it's oxygen or carbon dioxide, as we see in these images, because they're really just bouncing around like little billiard balls on a pool table. So if you're going to have the same temperature and pressure with the same volume, well then you should have the same exact number of molecules inside that container. And that's basically what his law says, that if you're going to have those conditions, you need the same number of moles. So that gases are interchangeable is basically what he was saying. They don't have as much unique properties as you might imagine. Okay, this is pretty much true. It holds up under most circumstances. This leaves out chemical reactions. It's just talking about the state of matter when it's not reacting, by the way, but it works fairly well, at least at STP. So Avogadro's law states that equal volumes of gases at the same conditions, STP, contain equal numbers of molecules, or we measure them actually in moles. This was actually how the formula for water, H2O, the most famous chemical formula, was determined by Cannizzaro, and it might be hard to tell what kind of relationship is shown here, because this doesn't look like the other 3 gas laws we've seen. Doesn't look like Boyle's law, doesn't look like Charles's law, doesn't look like Gay-Lussac's law either, because it doesn't have condition 1 and condition 2, because you can't really change the temperature or the pressure here, so it's really just relating volume and moles at those exact conditions. So it might be hard to see here, but this is actually a direct relationship. Volume is directly proportional to the number of moles of a gas. The easy way to think about this is, well, what if n is 1? Then it's 1 times k, and then the moles will cancel, and you'll get 22.4 liters. Well, then what if n was 2? What if you had 2 moles? Well, then it's 2 times k, and the moles cancel, and you get 44.8 liters. So notice that we just doubled the moles, and we doubled the volume. Well, just from that alone, you should be able to see that that sounds like a direct relationship. Here are 2 examples of how Avogadro's law can be used. The first one is just the simple use of the formula to determine the volume of 10 moles of an ideal gas at STP. We'll talk about why I'm saying ideal gas in the next notes. So basically that's just N would be 10 moles. K was, 22.4 liters per mole. So we multiply those together. It's really just 10 times 22.4 moves the decimal over 1. And then, of course, the moles are going to cancel there. So you're going to be left with 224.0 liters. That's a pretty obvious direct relationship. If you have 10 moles, you're going to have 10 times the volume, so 22.4 times 10. All right, but the tricky way to use Avogadro's law is when you try to determine the molar mass of a gas. This, again, was one of the original ways that molar masses were determined. So look at this. A 10-liter sample of a gas has a mass of 19.2 grams at STP. The molar mass of the gas is. So if we're going to determine the molar mass of a gas, well, we need to know two things. We need to know the grams, and we need to know the moles. Well, notice that in this question, it gives us the grams, so all we really need are the moles. What's the letter in that equation that stands for moles? Oh yeah, it's N. And it's actually giving me 10 liters. Which letter in the equation, which variable does the 10 liters go in? Oh, that's the V. So if you think about it, it's 10 liters equals Kn. Oh, so if I divide both sides by K, well then I get 10 liters divided by 22.4 liters per mole. And that should give me N, right? And it does. So 10 divided by 22.4, well that's going to be something around a half, around 0.5. It's a little bit less than that, 0.45 moles. So if we know how many moles we have, now notice 10 liters is less than half of a mole box. So of course, it's got to be less than half of a mole. And this only works again at STP, but now we've got the moles, and it already gave me the grams. Well, guess what? Molar mass is grams per mole. So if I divide the number of grams we have by the number of moles we have, like so, that will give me the molar mass of the gas. So 19.2 grams divided by 0.45 moles, that will give me 42.67 grams per mole. And then I could look on a list of molar masses and figure out what gas or what mixture of gases that must be to have that molar mass. We'll talk about the mixture part later. But this is one of the ways that molar masses were originally determined. Now that's a little tricky. I understand that the bottom one is a little bit hard to follow, but at least the top one should be very straightforward. That's normally the way we mostly use Avogadro's law. To determine the volume of a certain number of moles, it's just N times K, and boom, you've got the V. So now we have learned about 4 gas laws, what I like to call the little ones, and now we have everything we need to put them together for the big one, the real one. The 5th equation we're learning is in the next notes.